So is it visible in your screen?
Yeah.
Yeah.
Yes.
Good. So just a recap, as we were discussing, I would like you guys to prepare a component drawing, which basically should have the front view, the side view, the top view with all the information in there about fabrication of that part, along with an isometric view at a corner, which can be at the bottom right, top right, whichever um, space or whatever space is there for you in your drawing, you can use that. So I want an isometric view of the part, the front view, side view, and a top view, along with all the information. I mean, dimensioning, along with any other information that you think needs to be there for the fabrication. So that is the component level drawing. I'm sure you guys will have different components. Now there will be some group where you are not fabricating any component in a traditional machining process. You may be using 3D printing, but even in that case, you need to prepare the drawing as if you are assuming that this part is going to be fabricated in the machine shop. So even if your components and your assemblies are going to be 3D printed, it's not you should have the only the CAD model of it. You should also prepare the drawings for it, assuming that you do not have access to 3D printer and they are getting fabricated as per the traditional machining processes. So you must have the component drawings for your project. Along with the component drawings, you should have sub-assembly drawings and assembly drawings. So this is a top-level assembly, which basically shows the label for each individual component. Now, here I'm not showing any individual details of the individual components, but what I'm showing here is a bill of material. As you can see in the top right corner, there is a table which contains the item numbers, the labels, what is the part number, what is the description. The description is blank here, but you need to provide a description about specifically what that part is going to do, short description and amount of parts or the quantity that you are using in that assembly. So that is a top level assembly drawing, which basically contains the information of all the parts that are going to be there in your design. Now here I have not shown the exploded view. If you can provide an exploded view with the numbering labels, that would be even more better. But at least you must have the part labels and the information about them. And that is basically what I refer to as bill of materials. So you need to have this information at the top level assembly drawing. And you need to also have sub-assemblies. So when I say sub-assemblies, for example, here you see part number 2 and part number 3. So part number 2 is a motor mounting assembly bracket, with L-shaped bracket, as you can see. And part number 3 is a motor. So you basically need to assemble part number 3 on part number 2 using some fasteners. So you need to have a separate drawing of showing that how these two parts are getting assembled together. So that is what we call as sub-assemblies. So the purpose of the sub-assembly is that once you have fabricated the parts or procured the parts, how are you going to do the assembly? What is the sequence of assembly uh, to be followed by a person so that you can get the top level assembly, or you can basically assemble the whole design. So the purpose of the sub-assembly drawings is to make sure that you have provided enough information in the drawing that will help the reader to assemble the parts or disassemble the parts easily. So that is the information. I mean, the drawings should be prepared with that intent in mind. And the individual component drawings, the purpose of that is that if I go back the slide, so the purpose of this individual component drawings is that it must have all the dimensions, all the datums, all the references, all the tolerances that are required to fabricate it individually. So those are the two different, there are two different purposes of these drawings. So individual component level drawings uh, should be made for the purpose of fabrication, excuse me, and sub-assembly drawings and assembly drawings have to be prepared for the purpose of uh, assembly and disassembly operations. Does it make sense to you guys?
Yeah.
Yeah, that makes sense.
And if there are any questions, please let me know. And as I have said, that there are some groups where you are not fabricating as per in a traditional definition of fabrication or machining. So you are not using any machining operations and anything else, but you are using some 3D printing, or you basically are using some commercial off-the-shelf products, or you're assembling them together. But nonetheless, whatever the mode of operation or whatever the mode of assembly you're using in your project, you have to follow this sequence of creating the component level drawings, creating the sub-assembly drawings, and creating the top assembly drawings. And that is what needs to be there in your CAD submission, so which is due soon. So the drawings basically are I mean, the information that you are going to provide should have these details. Any questions from anybody so far? Okay, if none, then as we were discussing last week, we are going to recap our discussion about geometric dimensioning and tolerancing with few examples from the textbook. So here I am just recapping some of the principles. So,
Professor,
yes.
someone asked a question in the chat. They said, "Do you want CAD drawings for parts we're ordering for from McMaster?"
Uh, Let me see. So if the parts are going to be procured from off the shelf, then it depends on whether the drawing is available to you or not. But I would ask you guys to include the drawing if they are available from McMaster. McMaster generally have the drawings available for most of the parts and components. So please include the drawing. Some of the suppliers may not provide you the drawings. So if the drawings are available, please include it in the set, in the complete set of submission.
Okay, thank you.
Yeah, welcome. Okay, so other than that, okay, so what we were basically trying to do here is to recap some of the information about GD&T, and we'll take a couple of examples from the textbook as I was mentioning, and we'll see if we can go through some of we can understand the symbols, and we can answer some of the questions as are there in the unsolved problem sets of your textbook. So we'll see that. Okay, so before we actually do go through those examples, last week there was one question that how will we check the perpendicularity of the axis? So I actually post one reference in the Beachboard which talks about GD&T symbols, and it basically gives a very useful information about the different symbols, how to manufacture and how to inspect. So if you are interested, you can basically go through those details, and you will actually get to see and know how the perpendicularity is measured, the flatness is measured, and so on and so forth. So you guys can get that information from there. To recap some of the concepts that we were learning. So rule number one is envelope principle. It basically says that even if you do not have any GD&T symbol in your drawing, the rule number one or envelope principle states that you should have perfect form at MMC. MMC is a maximum material condition for this pin or the cylinder with the diameter shown as 20 plus minus 0.5. We know the maximum material condition will occur at 20.5 millimeters diameter. And basically it means that whatever the form of the cylinder is, it can have some curvature, it can have some bend shape, but as long as it remains within 20.5 millimeter diameter, it is perfectly acceptable. So that is what is rule number one says. Then there was some discussion about the datums. So here I mentioned that we have to be very clear about what the datums are, what is datum feature, and what is datum feature simulator. So datum feature is a physical surface of a part. So it is basically, if you see this L-shaped bracket with a hole on the top surface, and the bottom surface is basically one datum feature, which is basically a non-ideal physical surface of the part, which we call in a drawing as a datum feature. Now, by referencing that feature as datum, what we mean is that we are going to place a bracket on a feature simulator, which can be a flat surface plate, which is highly polished surface. It can be a gauge pin, a machine tool bed on which we are placing the part, and that the top surface of that top of the surface plate is simulating the datum of the datum that is simulating the datum of the feature. So the feature is the bottom surface, the datum is a plane, ideal, which is a theoretical plane. Theoretically, um, it is used to establish or reference the dimensions and measure different dimensions. So we are basically measuring and inspecting the height of the block and perform different measurements using the surface of the surface plate, which will be our datum feature simulator. So those are some of the uh, descriptions we should basically keep in mind. Similarly, if the datum is an axis of a hole, then the datum feature is basically an actual physical surface, which is surface of the hole. The axis of the hole is obtained by putting a gauge pin, which is a highly polished gauge pin inside that hole, and see what is the maximum diameter pin that can be inserted into it, and the axis of that pin will provide the reference about the datum axis. So those are basically some of the concepts we should keep in mind while implementing or understanding GD&T symbols in a drawing. Any questions so far from you?
No questions.
Everybody's following it so far?
Yeah.
Yeah.
Good, thank you. So we first start with this first example problem. This is the example problem 2010 from the textbook. So it basically gives you a drawing of a part and it has got different UD&T symbols in it. And there are certain questions associated with this drawing. So I'm not going through all the different questions, but I'm just picking some of the different questions that actually provides us good practice of interpreting the symbols and understanding what the drawing is. So if you actually look at this drawing and if the question is what is the maximum and minimum diameters for the cylindrical box, what would be the answer for that? So you can see here it has got a hole, cylindrical hole at the top, and you have a cylindrical box or an extruded part, which is actually shown here. If you can see the cursor that I'm moving in the screen. So that cylindrical box has got a specific dimension. And if somebody asks you what is the maximum minimum diameter of that part would be, what would be the answer there?
Which one, Professor? The circle you said?
The cylindrical box, yeah, this part.
That would be 30. You said the maximum, right?
Yeah, max and minimum diameter of that.
30.1.
This one, cylindrical box.
Oh, sorry, 50.3 would be the max.
Yeah, and minimum is 49.7. So everybody, I mean, that is pretty simple and straightforward. Now, the complexity arises when somebody would ask that what is the effect of this position tolerance on the diameter? So let's say if I have a position tolerance of 0.2, what will be the maximum diameter of the hole would be in that case? Anybody, any guess? Are you guys getting the question or it's not clear at all?
Can you say the question one more time?
Yeah, so the question is, what will be the diameter of this cylindrical part would be for the position tolerance that is shown here? 0.2 millimeters, if I assume that all the dimensions are point or millimeters. So if it is 0.2 millimeters, what would be the maximum diameter in that case for the cylindrical part?
Be 50.2.
50.2. Any other?
49.7.
49.7. That's the maximum diameter you're saying, right?
Yes.
Okay. Any other thoughts regarding that?
50.5.
Okay.
would it be 50.1?
Okay, anything else? I mean, there are so many answers that I am not getting any consensus. So far, whatever responses I get, 4 or 5 responses, they all are different. 49.7, 50.1, 0.2, 0.3. So if I get any other consensus in this, then I will actually start describing or basically trying to see where we should, how should we actually interpret that.
50.2.
So okay, there's a consensus on 50.2, at least 2 votes on that. Anything else?
49.5.
Okay. So let's see how we can interpret that. Let me actually share a document camera here. Just give me a second, please. Okay, so can you see the document camera?
Yes, we can.
Yeah.
Okay, great. So here basically I'm just not looking at that drawing. I'm just looking at this simple projection of a cylindrical object. Here is a cylinder. It has got a circular cross section. It has got a specification of the diameter, and it has got a GD&T symbol, which we call as feature reference frame. So this is basically a feature reference frame. And in this frame, we know the first compartment provides a GD&T symbol, that amount of the specific type of tolerance we are using, the amount of tolerance. This is a modifier, material condition modifier. M basically stands for maximum material condition. A, B, C represents datum planes. So in this case, there is no A, B, C in here, as you can see, but I'm just focusing on understanding the effect of this tolerance on the diameters. So everybody agrees that the minimum diameter for this is 49.7. If everything is in millimeters, that's the minimum diameter. And the maximum diameter of that cylinder should be 50.3 millimeters. Everybody is with me so far?
Yes.
Yes.
Yeah.
Great. So the effect of this specific reference frame, what it is saying, that it has got a position tolerance. So this is a circle with one vertical and one horizontal dashes. So what is saying? It is saying that there is a position tolerance associated with the axis of this circle or cylinder. So axis is this, and the position tolerance of the axis is having a diameter of 0.2. What it basically says that my axis basically can lie in a circular zone of diameter 0.2 millimeters. So this has got a diameter of 0.2 millimeters, and within this diameter, my axis can lie like this, or it can lie like this. As long as the axis lies within a diameter of 0.2 millimeters, I have a perfectly valid cylindrical object. So cylindrical object can be, it may not be have a perfect form. It can have a bent shape. It can basically be like this. So I can have a cylinder which looks like this. And here the axis is basically lying within a tolerance of 0.2 millimeters. So it basically can have an offset from the perpendicularity. So if you basically see, this is the datum plane. From this datum plane, if this is a theoretical axis, which is perpendicular, perfectly perpendicular, I can have an offset from perpendicularity of 0.2 millimeters. Basically, the offset from perpendicularity will be contained within the cylindrical zone of 0.2 millimeters diameter. Do you see what I'm trying to say here?
Yeah.
Yeah.
Yeah. So my cylindrical object need not be perfectly straight and perpendicular to this datum. It can have an orientation. It can have certain angularity, or it can be away from the perpendicularity, as long as the axis of this cylinder lies within a cylindrical tolerance zone of 0.2 millimeters. Does it make sense?
Yeah.
Yeah. Along with, so that is basically the meaning of the tolerance, this feature reference frame. Now ABC references to the datum. So A basically means this is the A datum. Basically, this is the datum which is inverted triangle. So this is A. So with this with this respect to A, datum A, it should be perpendicular. There is no need for B and C if we are just looking at this drawing. So with respect to this datum A or this face, I should have the axis which is controlled by this tolerance zone, which is 0.2 millimeters. Now, let me know if you guys are able to understand this much information or important or able to interpret this much details that we
Yeah.
Everybody is with me so far?
Yep.
Yeah.
Yeah.
Any
Uh,
questions from anybody?
Yeah, so Professor, although even if the diameter wasn't completely in the center,
Mhm.
but the actual diameter of this, sorry, if the axis wasn't completely in the center, like if it was, let's say it was kind of diagonal,
Yeah.
would that affect the outside diameter of the circle, or would the circle still be like, let's say 50.1?
Yeah, that's a perfectly valid question and very good question. That's what I was basically coming in the next part. Is once we understand the importance of this tolerance zone or what is the amount of tolerance we are providing. Now, as you can see, now the cylinder is not perpendicular. So basically, that means it is now oriented at a specific angle to my datum A, which is this datum A. So at every section, if I actually measure in that section AA, or if I take a section here BB, if I take a section here at CC, any section wherever I actually try to measure the diameter of this hole or cylinder, it has to satisfy this restriction. So at any section, this diameter has to have a minimum diameter of 49.7 and maximum 50.3. It cannot go below this or exceed this at any section wherever I'm inspecting. So I'm inspecting at here using my vernier caliper. I measure this 50 millimeters. I say good. If I measure at this, I measure 49.8 millimeters. It's good. If I measure it here, it's 50.2 millimeters. It's good. So as long as at every section, the diameter is remaining within this range, the range of the allowable variation in the diameter. So as long as at every section my diameters is within this range, this part is perfectly acceptable. What this rectangular frame is saying, it is basically saying what is the amount of offset I am allowing from the perpendicularity. That's it. It's not, this information is not affecting the size. So this is basically a size dimension. This is a size dimension, and this is basically the amount of tolerance you are providing. Amount of tolerance. Amount of tolerance does not affect the size at any time, though the size do affect the tolerance. So size affects the tolerance, but a tolerance, amount of tolerance does not affect the size. Does it make sense to you guys?
I have a question.
Yeah.
Yeah, go ahead.
So your part can't sit anywhere beneath those 0.0 or the 0.2 millimeters. It has to be outside of it.
Which part? So this part,
The axis.
yeah, the
You know how there's
axis, yeah, axis should lie within a 0.2 millimeters.
when would, I
Yeah.
kind of don't understand that one. Can you show us a situation where it wouldn't work?
Where it wouldn't work. If the axis lies outside this cylindrical tolerance, then you do not have basically this specific constraint being meeting here in the drawing. You are able to see or not
I'm
at
just
all?
I'm a little bit confused.
Okay, let me actually try. Let me try with a different. So I'm now not saying a cylinder here. I'm basically referencing a hole. So at this point, I mean, the same thing will be applicable to the cylinder. So just for the sake of the discussion here, I'm referencing a hole here. So at this, in this drawing, you can basically see the hole has got a perfectly perpendicular orientation with respect to datum A. If that is your datum A, this space is the datum A. And this is your axis. Agreed? I mean, you are following this much part?
Yes.
Okay. So now if I say that I have the part looks like this. This is again a datum A. And now the axis of the hole is slightly offset. For example, imagine that you are drilling it and somehow the drill gets offset and it's not perpendicular at all. So now you actually have a drilled hole which is like inclined like this. You are getting this much part as well, information
Yes,
as well.
I get
Okay,
the part.
great. So how will we measure the offset of the axis? So what we are going to do, we are basically going to insert a dowel pin that is perfectly smooth and having a perpendicular orientation. And this is basically a gauge pin, which has perfect form, almost perfect form. So this is a gauge pin. The maximum diameter of that gauge pin is inserted such that it maintains a perpendicular orientation with respect to datum A, and the axis, the center point at the top and bottom will define the axis, the true axis.
Okay.
Right? Now from the true axis, I can measure how much offset the axis of my machined hole has to be, right?
Yes.
Or yeah, and as long as this axis, orientation of this axis lies within a tolerance zone of 0.2 millimeters, this part is acceptable. If the orientation of the axis is offset from away from 0.2 millimeters, that means it is not acceptable.
Okay, I understand when you talk about the holes, but not the outside part.
Great. So in this case, the thing is that just like we have the gauge pin here, we will have a gauge block now. So instead of a gauge pin, we will have a perfectly formed gauge block that will be like this. That is perfectly machined. That has got a perfect form of the hole. So this is a gauge block that we are going to use to measure the orientation of this cylinder. So this is a gauge block. Now, in this representation, you are basically seeing the cylinder is perfectly fitting inside the gauge block. Now, if this is the orientation of the cylinder and my gauge block comes out to be like this. Now, I will have the gauge block of different sizes. Of course, this gauge block will not fit in this. Do you see what I'm saying here? Now,
Yeah.
the true axis of this gauge block will define the theoretical axis, and you basically, of course, you can basically measure the high points and you can see how much offset this axis is.
Thank you. I understand it.
Got it?
Yes.
Great. So the important part is about how will we measure the orientation. So using, if it is a cylindrical pin, then you need a gauge block. So it is basically, we actually covered one topic about actual mating envelope. So this is basically called as actual mating envelope. So for cylindrical parts, the actual mating envelope is defined by the gauge block. For the holes, the actual mating envelope is defined by the gauge pins that we are going to use to measure the orientation or offset of the axis. Actual mating envelope. Make sense to everybody so far?
Yeah.
Okay, great. So if everybody is following it so far, let me go back to our original discussion, and that was that what would be the maximum diameter corresponding to this tolerance zone. So now what would be your answer?
50.3.
50.3. The maximum diameter will not change based on the amount of tolerance you are providing on the axis. The axis can have orientation like this. The axis can have orientation like this. But as long as at every section, wherever, whether it is section AA, section BB, whether it's section CC, at every section, your diameter lies within this size or tolerances, then the part is acceptable. And we know the maximum diameter would be 50.3 in that case. It cannot go beyond 50.3 at any section. Everybody is following it so far? Let me know if you have any questions or if you have still any confusion. I will try to explain again.
Makes sense.
Everybody is okay?
Yeah,
Yep.
we're okay.
Great, good, thanks. Now, I was making a statement here that the amount of tolerance does not affect the size, but the size dimension does affect the tolerance. So what does that mean? What that statement means? So imagine that you have this specific information about the circular cross section of the cylinder. And the reference frame, feature reference frame has position tolerance symbol, and the cylindrical amount of tolerance is given at 0.2 millimeters and datum is 0. So it does not have any symbol like here, M. It only does not have any symbol, it just has 0.2 millimeters. This is option 1. Option 2 is you have the same thing, but with a material condition modifier as M, datum A. That's option 2. And the third option is you have this position tolerance, you have this diameter, you have this modifier condition, but L, not M, it is L. L is least material condition, maximum material condition. You guys probably know by now. So option 3, M stands for maximum material condition, maximum material condition, and this is least material condition. So let's say if I ask you maximum diameter of the cylindrical part, everybody is agreeing it is 50.3 millimeters, 50.3, 50.3. Maximum diameter of the cylinder part does not depend on the way you are providing the tolerance zone. Whether you're using option number 1, option number 2, option number 3, it does not affect the maximum diameter. But what about the tolerance? So here in this case, option number 1, what is the tolerance zone? So what is the tolerance of just give me a second, please. Somehow I replace the cap of the things. Okay. So the tolerance zone is basically is this, where the axis would lie. The axis can orient in any fashion, as you can see. It can orient in any fashion as long as it remains within a cylindrical zone of 0.2 millimeter. That's a cylindrical zone for the orientation of the axis. The axis can lie anywhere in that cylinder. So that is the diameter of the tolerance zone. Option number 1 saying that this tolerance zone has got a diameter of 0.2 millimeters, irrespective of whatever the size is. If the size of this cylinder is 50 millimeters, the tolerance remains this. If the size is 50.3 millimeters, then also tolerance remains this. If the size is 49.7 millimeters, then also tolerance remains this. So this option 1 is called as regardless of feature size. Regardless of feature size, or RFS. Basically, irrespective of the size, the tolerance always remains 0.2 millimeters of diameter. Cylindrical tolerance zone of 0.2 millimeters, also called as regardless of feature size. Now, coming to this, what does this M stands for? Maximum material condition. Everybody agrees?
Yes.
Yeah. Maximum material condition happens for the cylindrical object at 50.3
Can you repeat
millimeters.
that?
So, okay, we are now discussing option number 2. So option number 2 has got an M modifier here. M modifier basically means maximum material condition. Agree? Yeah.
Yeah.
Yeah. And the maximum material condition for this cylinder would happen at what type? At what size? 50.3 millimeters, right? That will be the maximum material condition. Are you agreeing?
Yes.
So what this option number 2 is saying that my tolerance zone will be 0.2 millimeter diameter when it has got a maximum material condition, which is 50.3. Now, if I'm just looking at option number 2 only, if my diameter is 50 millimeters, what would be my tolerance zone in that case? The tolerance would be 0.3 plus 0.2 is 0.5 millimeters. So this is the bonus tolerance we actually get because of our size. Our size is deviating from MMC. This is my MMC condition. I am deviating from my MMC by 0.3 millimeters. That 0.3 millimeters is added to the actual tolerance amount, which is 0.2 millimeters. So this 0.3 is added to 0.2, and what I'm getting is total tolerance zone is 0.3, 0.5 millimeter diameter. So this is a bonus tolerance, dia 0.3. Dia 0.2 was the actual tolerance at MMC, and that the total tolerance will be 0.5 millimeter diameter of the cylinder. Cylinder will now be bigger at 0.5 millimeters. Let me know if you guys are following it or not. If not, I'll try to explain again. So this modifier is basically saying I will have the tolerance zone of 0.2 millimeters, this diameter of the cylinder where my axis can lie and can orient will have 0.2 millimeter diameter when the part is fabricated at its MMC. The part is fabricated at its MMC, which is 50.3. At 50.3, my tolerance zone has a diameter of 0.2 millimeters, which is this. This is a tolerance zone. If my part is fabricated at less than MMC, let's say 50 millimeters, then I got a bigger tolerance zone. So that bigger tolerance zone basically says that is obtained by adding the amount of deviation from MMC to the tolerance zone that you have been specified. So that will be added, and what you actually got is the total tolerance of your axis. Still, it is basically the tolerance of the axis. That means I am now having a bigger tolerance on the orientation of my axis. 0.5 millimeters of diameter. Let me know if it makes sense to you.
You're still on the max material, right, Professor?
Yes.
Oh, okay. No, because I was writing down, so I
So this is not MMC. This is away from deviation from MMC. So if I am at 50 millimeters, that means I have deviated from my MMC. This is my MMC. This is not MMC. This is basically deviation from MMC by 0.3 millimeters. So that 0.3 millimeters gets added to the tolerance of 0.2 to get a total tolerance of 0.5. So that is your called as bonus tolerances. If the part is fabricated at 49.7 millimeters, then the bonus tolerance would be 0.6 added to 0.2. So that will be the total tolerance zone that is acceptable to the designer. So what we are actually seeing here that the tolerance is getting affected by the size of the part. So if the size of the part is at MMC, I have got this much tolerance. If the size of the part is deviating from the MMC, it's still within our tolerance range. Minimum diameter is, remember, 49.7, maximum is 50.3. So I can vary my diameter from 49.7 to 50.3. So basically this is perfectly acceptable part for 50 millimeters diameter. But what it does is that it increases the tolerance zone of my axis. Now, physically, what is happening here? So physically, let's see what is happening. So if my part is made at 50.3 millimeters, so let's say this is my datum. This is the part fabricated at 50.3 millimeters. In that case, I have a very tight tolerance on the axis. The axis cannot orient more than 0.2. So I cannot have the cylinder offset more than 0.2 millimeters. But if my part is getting fabricated at 50 millimeters, then I have a much further leeway in accepting the out of tolerance of the axis. The axis can further be away from the perpendicularity by a larger amount because my part is fabricated at less than MMC, which is diameter, let's say 50 millimeters. Then in that case, my axis can lie within a cylinder of 0.5 millimeters. So I can have, I can accommodate offset of the perpendicularity of the cylinder if it is fabricated at lesser dimension than at MMC. If it is at MMC, that means I need to have tighter control on the axis. If it is less than MMC, then my axis can have more offset from what it would have been at the MMC. Let me know if it makes sense to you. Remember the gauge block, which actually is getting fitted here. This is the gauge block. Similarly, this is the gauge block. The gauge block dimensions are not changing. So let's say the gauge block dimension is 50.5 millimeters. So the gauge block that is fixed. That is basically always 50.5 millimeters. So the gauge block is the same gauge block here. Same gauge block here, 50.5 millimeters. But I have a pin which is 50.3 millimeters and I have a tighter control on the axis. But if my pin is smaller, then I can orient the pin and can have more clearance, and it can have it can have offset from the perpendicularity, more offset from the perpendicularity can be accommodated. Let me know if it makes sense to you.
Yes.
Yeah, are the same gauge block, 50.5 millimeters internal diameter, and I mean there's a clearance, of course, fit between the pin and the gauge block. But if I am fabricating this part, the pin at a smaller diameter, I can accommodate more offset from the perpendicularity. That is what this bonus tolerance is actually showing. Make sense? And if I reduce the diameter to 49.7, I can further accommodate tolerance or offset from perpendicularity by this much. And this is what we call as bonus tolerances. Basically, what is saying that if my part is not at MMC, then I am basically going to affect the total tolerance I am going to get. So that is what this modifier is affecting. Now, similarly, if I have a least material condition, that means it will affect the sizes or tolerance in the reverse manner. So least material condition means at 49.7 millimeters, I should have a tolerance zone of 0.2. And then as I deviate from the least material condition, my tolerance gets affected by the actual size.
So adding on to that, Professor, like let's say you're using the least material condition.
Mm-hmm.
If you were at 50.3, then your axis has no tolerance.
Okay, let's say let's actually do that. So 50.3, 50, 49.7. 49.7, I have 0.2 diameter tolerance. No bonus tolerance in there. At 50, I am offset from least material condition by 0.3. That's get added to 0.2 and I get 0.5 in here. Total tolerance. This is total tolerance. Total tolerance This is bonus tolerance. This is actually specified tolerance. And at 50.3, I'm offset from 0.6. It's get added to 0.2, and now the total tolerance will be 0.8. So it basically goes in the reverse fashion. So earlier I was getting 0.8 millimeter of offset for 49.7, but if I'm using LMC, then I am basically going in the reverse fashion.
Okay, that makes sense.
Yeah. Anybody has any questions? Everybody is good so far?
Yes.
Okay, great. So
Yeah.
everybody is following it, and if there are no, I mean, if there are any questions from anyone, please ask. I will try to explain. I mean, I may not be able to fully explain or make you understand. I will try my best to explain the situation or whatever confusion you may have. Okay. So if there are no other questions, then I believe one of the other question that will arise is that if I actually go back to the slides, okay, so in this, if somebody asks you if there is any GDNT symbol that controls the form of the cylinder, I mean the form of the cylinder means it does not have any bent shape, or it basically has a perfect form. There is no such rough edges or something like that. So if there is a form, is there any control that affects the form of the cylindrical piece here? Any symbol in here?
First.
Is there any symbol in here you think that affects the form of the cylinder?
Talking about the M?
M stands for maximum material condition. That's it. That, so, I mean, yeah, you are going in a right direction, but I'm just,
Sorry, like, what are you asking? I didn't really catch that.
so form of the cylinder. So cylindrical form. Remember, or if I go back, so if let's say cylinder is like this, having the curvature like this. So is there any control in the drawing that that controls the curvature of the cylindrical part? In this drawing, do you think there is any symbol that controls the cylindricity? I mean, to be more precise, the form of a cylinder is called a cylindricity. Is there any control that affects the cylindricity of the part?
Is cylindricity? Oh.
Yeah, is there any tolerance that you are seeing, or any symbol that actually shows here which shows the cylindricity?
No.
No. So in the absence of any control on the form, you always have to remember that rule number 1 applies. And remember rule number 1, what does it say? It says that it should have a perfect cylindrical form at its MMC. Rule number 1, envelope principle. Okay. So basically what it means that at 50.3, at any section of this cylindrical piece, you cannot have a diameter more than 50.3 millimeters. That's what this cylindricity is basically controlled by. Or if I go back the slide, it basically says that this is the envelope. So if you do not have any control on the cylindricity from the drawing, it basically says that the part is going to be fabricated such that it has perfect form at MMC. MMC will be 50.3 for our drawing that we were referencing. So at 50.3, I should have a perfect cylindrical part. I cannot have any curvature in the piece which exceeds 50.3 millimeters. Make sense?
So your faces, as long as your faces are 50.3, the like the inside doesn't really matter if it's curved or
Yes,
not.
yes. The inside can be 49.7, 49.8, 50, but as long as the external diameter is 50.3, I am okay. And 50.3 throughout the length, it is not only at one section. Throughout the length, it cannot have more than 50.3 millimeters. I'm not sure if you are, okay, so let me actually say if you have a gauge block on top of this, so the gauge block can have the maximum diameter as 50.3. You cannot accommodate, you should not require a gauge block with diameter more than 50.3 millimeters. Does it make sense?
Yeah.
So that will basically say that it has a perfect cylindricity. Cylindricity means circular cross section along the length. So I should not have more than 50.3 millimeters along the length. And how can I measure that? I will fit a gauge block that has got a hole of 50.3 millimeters. I'll fit that gauge block in that cylindrical piece, and if it fits, that means it has got perfect form. If it does not fit, that means the part is not acceptable. It's just like a block and plug. So you assume that this is a plug and you are using a block which has got a true form at 50.3 millimeters. And if the plug gets inserted in that block, acceptable. If the plug is not inserted in the block, the plug is not acceptable. Everybody is with me so far?
Yeah.
Cool. I guess the next example is the similar. I mean, it has got a similar set of questions, but what I am going to do, I'm not going to explain all the details, but I will let you guys look at the drawing and look at the symbols and let me know if there is something that you don't understand.
Professor, what are the like ABC? What does that stand for again?
A, B, C. Where you see this A, B, C? This is A. This is
Yeah,
B.
like let's just say like this top one on the left corner.
Which
It
one?
has,
This one.
yeah, it has ABC.
So
And
these are the datum planes. Datum
Oh,
A, datum B, datum C. Remember, this is a feature reference frame, rectangular block. It has got a position tolerance, and it has got two levels, level 1 and level 2. And basically, it has a different connotation. I mean, we have not gone through this explanation if we have two different levels. It basically says that you have a position control on the part itself, on this hole itself, and the group of holes that you are seeing. There are 4 holes in there. It has got 4 diameter 6. That means these holes are um, four numbers, 6 millimeter diameters, and you are controlling the position of these 4 holes together. So in that case, you are basically using 2 levels of feature reference frame. So I mean, these are generally used if we are controlling the orientation of all the different holes together. So we are not going through that level of description or discussion at this point of time. But if you guys are interested, you can always reference the text representing the position control of a group of holes. How can we control the position of a group of holes? So that basically level of compartment, 2 levels of this feature reference frame represent that.
what about the one that's under that one for the
Which
small
one?
one in the middle?
Which one?
Down, if you go down, that one.
This one.
Yeah, that perpendicular. Does that just mean that the axis has to be like perpendicular
Yes,
with the rest
exactly.
of them?
Yes. So what
Oh,
it basically says that this locating hole has an axis, which is your datum feature, because your reference frame is attached to a dimension. So you are basically representing the axis of this hole, and that has to be perpendicular to datum A. Datum A is the bottom surface of the plate. So this is the axis, and basically this is the axis of that locating hole, and that axis has to be perpendicular to datum A within a tolerance zone of 0.05 cylindrical tolerance zone.
Professor.
Yes.
For the top right, top left GDNT where B is at when datum B is at maximum
Mm-hmm.
material condition, is that when the whole or is that when the middle hole right there is
Yeah.
at maximum? Oh, is
Yes.
that
Yes.
minimum?
Yeah, is there a maximum material condition? The datum is corresponding datum axis. Datum is basically the axis of this locating hole. And when this hole is at its MMC, that is what basically referencing to datum
Oh,
axis.
okay. Okay. And the same with datum C when
Yes.
okay.
So this is basically you have a spot facing, which is this. Uh, Sink, counter sink of diameter 12 and has got a depth of 3 millimeters. And there is a specific size tolerance on that. Other than that, any other information? Let me see if that is, yeah, that's basically a counter sink there. So that spot facing that you are seeing, that is basically a recess that is formed. That is basically a symbol for counter sink of diameter 12 with a depth of 3 millimeters. Any symbol that you are seeing here which you are not understanding or you're not following?
I have a question.
Yeah, go ahead.
I looked it up in the book. It's called a counter bore. What exactly is that?
So counter bore and counter sink are basically two types of machining operations. So actually this is, just give me a second, please. I'm just looking at the symbols that are there for counter bore and counter sink. Let me actually open the.
Looks like countersink has an angle and counterbore is flat.
So counter bore is flat and counter sink has basically an angle. So basically you have this triangle. So this is basically a counter bore, not a sink. Sorry. So that is a counter bore, not sink. So let me actually open one of the symbols chart from my earlier presentation last week, which basically gives you the symbol. Just give me a second, please. Okay, so here, can you see the slide on the screen?
Yes.
So you can see the different symbols and the description. So counter bore basically means you are drilling a hole and that is a flat. When you have a spot facing, you're doing this facing of operation, then that is basically a counter bore. And if you have a taper or an angle or at the bottom, then it basically called as counter sink.
Okay.
Got it? So these are basically two different type of machining operations. So if you have a flat face, that's counter bore, and if it has an angular face, basically it's a blind hole you are making, then you basically have a counter sink. And if it has got a spot flat face, it's counter bore. That's the difference.
Okay. Thank you.
You're welcome. That's not counter sink, it's counter bore actually. And these are basically saying it has got a diameter 12 millimeters and a depth of 3 millimeters. That's it. So is everybody with me so far? Any questions? Anything you guys think that any information that you are seeing here which you are not able to understand? Please let me know.
I have a question again.
Yeah, go ahead, please.
The M, why is it on the B and the C at the top?
So these are basically representing the modifier symbols for datums B. So you have a modifier for the tolerance zone and you have modifier for the datum B. So how the datums are defined. So this is basically saying that this feature control frame is saying that I have perpendicular to datum A and the datum B and datum C are defined at the maximum material condition when the parts are fabricated at its maximum material condition.
Okay.
Yeah. Now, how this, I mean, we had just seen that how the modifier symbols on the tolerance zone affects the amount of bonus tolerances. So basically it says that when the part is fabricated at its maximum material condition to be 11.8 millimeter, then I have a 0.3 millimeter of tolerance zone, and then I will keep on having the bonus tolerances. Now, how the bonus tolerances are getting stacked up with these planes, I am not sure at this point of time to explain how to explain the modifiers symbols. I mean, if it is not at my how the datums will be defined. So I will come back to that description probably in the next lecture. I have to look at that how the tolerances will be affected if my modifiers are attached to the datum planes. So I am not sure at this point of time to explain. What if it is not at MMC, how the datums will be affected. So we'll come back to it, come back to this description later. Okay. Any questions, anything else, guys? So if not, then actually we now move past the discussion from GD&T. Basically, we have, I mean, you guys have basically got enough information to interpret the symbols, interpret the GD&T symbols and any drawing, and um, uh, basically understand what the drawings are telling you, what the symbols are telling you, what the tolerances, amount of tolerances are telling you. So there will be one or two examples in your homework as well to give you some practice. But having said that, now we actually switch back, switch our gears from the discussion on GD&T to the design of individual components. So we will start with our discussion on limits, fits, and tolerances once again. And that is basically the last topic about the transmission shafts, like how the fits and tolerances are, or how the tolerances affects the fits, or how the limits affects the fits. So how can we specify what type of tolerance we need to provide in our drawings if you would like to have a clearance fit, or if you would like to have an interference fit. So before I actually go and look and show you the specific slides, which we already have seen, I will switch back to document camera again, just to give you a recap of what what those tolerances basically mean, what the fundamental deviation means, and what the other charts actually have. You already have the slides from the beach board, so you can access them. What I'm actually showing here is how to interpret the specific symbols in there. So what we are referencing here, or what we are trying to basically have our discussion is on interference fits. But before we actually go in there, let me actually discuss about the fundamental deviation and basic size.
Look at this, look at this. How's everybody?
So this is the basic size, which remains the same for shaft and a hole. So we have a shaft or made of another one component here and another component which is basically has a different tolerances, which basically say that there is a clearance fit between these two parts. Now this deviation from the basic size is called as fundamental deviation. So this is the fundamental deviation for the shaft, and this is the fundamental deviation for the hole. Fundamental deviation from the hole. So these fundamental deviation, the deviation from the true size or the basic size, is represented by letter symbols. So these fundamental deviations for shaft and hole are represented by letter symbols. C, D, G, H, N, P, so on and so forth. So they each letter symbols have a specific amount of deviation that is provided in your tabular chart. So you can, I will basically show, or in the slides, you can basically see that there is a tabular chart which shows the amount of fundamental deviation for a given size of the range of the size of the shaft. So you will basically see an amount of deviation for, let's say, 0 to 3 millimeters. What's the deviation for letter symbol C, D, G, and H? H has a deviation 0. So let's say from 4 millimeters to 10 millimeters. I don't know. I'm just making up these numbers at this point. I mean, you can refer the chart and see for different size of the shaft, each letter symbol has got a specific amount of deviation. So this is negative deviation. So let's say it's negative 0.1, for example. And after H, it is positive. So this is positive. So negative basically means that I am lower, I am basically, the shaft has a deviation in this direction. That means the shaft has got a diameter less than the basic size. That is what negative deviations mean. Positive means that if I have a symbol N, then basically means the shaft is now having a diameter bigger than the fundamental deviation or bigger than the basic size. So for the holes, the letter symbols that are used are correspondingly bigger C, D, G, H, N, P, and so on. These have the same way of referencing. So you have basically the size for 0 to 3 millimeters. There's a specific amount of, let's say 0.1 here, 0 for H, and 0.1 millimeter for. These are basically the range of deviations for the whole system. Now, let me know if you guys are following it or not. Is everybody following it, what I'm trying to explain here?
Yeah, we're following it.
Yeah.
Yep.
Just basically, if you pick a number, let's say if I pick a number 34 millimeter as my basic size. So the way that I mention, or I actually see the tolerances as represented 34H7P6. That is how you will actually see in the drawing any hole or any assembly of shaft and hole is referenced by this specification 34H7P6. What does this basically means? This 34 is your basic size. It basically says that my shaft and my hole has got a 34 millimeter diameter. Capital H basically stands for the hole, and the hole has got fundamental deviation as 0. So H basically means the fundamental deviation. That means the minimum diameter of the hole is basically 34 millimeter itself. So this is basically these two compartments. These two symbols are for hole, and these two symbols or these two letters are letter and the digit are for the shaft specification, hole dia specification, and shaft dia specification. Hole dia specification. 34H7. H is the fundamental deviation, and the other number that you are seeing here that represent tolerance grade. Tolerance grade means you have a minimum diameter and a maximum diameter. So the minimum diameter is given, or whatever that, whether it is minimum and maximum depending on whether you're looking at shaft or hole. So fundamental deviation is how much offset you are from the basic size, and on top of that, how much tolerance you are providing. So this is known as tolerance zone, given by these digits, which we call as IT7, International Tolerance Grade numbers, given by IT numbers, International Tolerance Grade numbers, International Tolerance Grade. So again, if you look at the table, there is another slide and in the PowerPoint presentation that basically tells you that what is the international tolerance 1 to international tolerance grade 2, international tolerance grade 3, 7, and so on. What is the amount of tolerance you are providing for a given size?
Professor, what is that symbol by the shaft diameter specification?
P6.
That's a P?
P stands for the fundamental deviation and 6 stands for the IT grade. So
Okay.
IT grade 6 here. P is the fundamental deviation. Here, the fundamental deviation is given by letter H, fundamental deviation, and IT grade 7 is the specified tolerance zone. Is everybody with me so far?
Yes.
Yeah. So if you guys are following it, or you following what I'm trying to explain here, can you guys look at those tables from those slides and let me know what would be the numbers corresponding to H? Obviously for H, the fundamental deviation is 0. And what is the number corresponding to IT7? Can you look at that and let me know what is IT7 for 34 millimeters correspond to? What is IT7 corresponds to, and what is IT6 corresponds to?
You should look at it where?
In the PowerPoint slides I just uploaded in the
Okay.
Beachboard, you will find the table for IT grade and also fundamental deviation. So what I would ask you guys is look at the slides and let me know what this number would be, IT6 and what is IT7 for 34 millimeters.
Would it be 0.016
0.016. Okay, and this is?
and 0.025?
Everybody agrees here, or is if there is anybody who does not agree, please let me know. I'm not looking at the slides. I'm asking you to let me know what the values.
I agree.
Everybody agrees. Okay.
Yeah.
Great. So what actually now we are going to use this information to find what is going to be the minimum diameter of my shaft, diameter of shaft, maximum diameter of shaft for our 34H7P6 specification, and similarly, what is the minimum diameter of my hole and what will be the maximum diameter of my hole. So we are going to find out that. And how to find that? We already know. Let's say we are talking about the hole now. For hole, it is H is a fundamental deviation. So that means the minimum diameter of the hole is how much? If you look at this is the basic size and this is the fundamental deviation. And this fundamental deviation you are seeing, this is basically going to be 0 because it has a corresponding letter H, which has got 0. So fundamental deviation is basically 0. So what is the minimum diameter of the hole would be? What is the minimum diameter of the hole would be? If my fundamental deviation is 0, that means the minimum diameter would be basically the same as my basic size, isn't it?
Wouldn't it be 34? You said minimum?
Yeah, minimum.
isn't it the minimum 34 minus the 0.025, or what is the 0.025 for?
Okay, so as I was saying, 0.025 is the extra tolerance. These are basically the extra tolerance you are providing from the fundamental deviation. Extra tolerance from fundamental deviation. So referencing back here, this is my basic size line, 34 millimeters. I am away from my basic size by fundamental deviation. And on top of that, if I add a tolerance, that will be my extra tolerance zone. So the IT numbers are going to provide my tolerance zone. So this is a tolerance zone that is basically getting added to my minimum diameter, right? This is the minimum diameter. This is the basic size. That deviation from the basic size is called as fundamental deviation. Now, if I have letter H, that means my fundamental deviation is 0. That means that minimum, this fundamental deviation for the hole is 0. That means minimum diameter of the hole is 34 millimeters. 34 plus fundamental deviation is 0. That means I have got 34 millimeters as the minimum diameter of the hole. Let's see if you guys are following it.
Yeah.
Following it?
Yeah.
If there is any confusion from anybody, please let me know. I will try to explain again. And if you guys are following it, can you help me to find the maximum diameter of the hole? It would be minimum diameter plus the amount of tolerance.
Wouldn't it just be 34 also?
No, I have IT7 here, right? IT7 for 34 millimeters 0.025. So that means
34
plus 0.025. So that means 34.025 millimeter is my outer diameter of the hole, the tolerance. So my minimum diameter is 34 millimeters, maximum diameter is 34.025. So remember, minimum diameter is given by the basic size plus the fundamental deviation. And on top of that, I am adding some more extra tolerance, which is given by IT7, which is 0.025. So this is the extra tolerance. Extra tolerance I am providing based on my IT number, the international tolerance grade number 7, IT7, which is this, which is, you said it is 0.025. So this is the extra tolerance from the minimum diameter. So minimum diameter is given by this number, and the maximum diameter would be on top of that, add the tolerance zone that you have as aligned. Let me know if you guys are following it or not.
Yeah.
Yeah. Is everybody following it or not? I mean, the reason I'm asking this question again and again, because this discussion will lead you or will lead us to our discussion on the next topic, which is interference fits, how to find the interference fits, and based on those fits, basically why those are important and what are the consequences of different types of interference fits. That's what we are going to learn. But before we actually go into that discussion, we should be able to determine what is the shaft specification and what is the hole dia specification. So are you guys comfortable with the hole dia specification?
Yes.
Yeah. So
Yeah.
can you guys help me for similarly for the shaft? So the shaft diameter can be determined by what? So if I refer to this, my basic size is 34 millimeters. And on top of that, I have to add my fundamental deviation. My fundamental deviation is given by this chart. Can somebody tell me by looking at the table what the P stands for? How much fundamental deviation for 34 millimeter corresponds? So 34 millimeters and P.
0.026 plus
Uh,
0.20.
plus 0.026. So
Yes.
this is the amount of fundamental deviation that my shaft is going to have. Now plus means this is plus for the shaft, this is minus for the shaft, fundamental deviation. So when I say plus, that means my shaft diameter is going to be, shaft diameter is going to be basic size plus the fundamental deviation given by letter P. So 34 millimeters plus 0.026. That is my minimum diameter of my shaft. And what will be the maximum diameter? Maximum diameter would be the minimum diameter, which is 34.026 plus the tolerance provided by IT6. IT6 is 34.026 plus 0.016, which comes out to be 34.042 millimeters. So I have got minimum of the shaft as 34.026, 34.042 as the maximum diameter, and same for the hole. So if I'm basically looking at my shaft, it has got the specifications as 34.
What?
Can you guys please mute?
What?
Somebody is not muting your mic and it is basically affecting the class. So can you please mute your mic? 0.026 plus plus 0.042. So that is a shaft specification, and the whole specification is it has got 34 0.000 to 0.025. So basically this is what we are actually getting based on our specification 34H7P6. Now what type of fit it is going to be with this configuration? So this is a shaft, and the hole basically represents the any specific component. It can be gear, it can be pulley, so it can be any component. Gear, it can be bearing, it can be hub, it can be pulley, it can be any component that is mounted on the transmission shaft. Now this is the assembly of a transmission shaft along with the machine component, which can be gear, bearing, hub, and pulley has got a hole inside it. And we are basically mounting this component on the transmission shaft. And these are the dimensions we got based on this specification. Now, what type of fit is it? Is it clearance fit? Is it interference fit? What do you guys think?
It'd be an interference fit.
Perfect. It will be interference fit. Everybody agrees?
Yes.
Yeah. So that is basically we are trying to learn here that the reason we are actually trying to have an interference fit is because we can ensure that there is no slippage between the rotation of the shaft and the rotation of this component, which can be gear, bearing, hub, pulley, or any component that is actually mounted on the transmission shaft. So the interference fits are useful to ensure that these two parts are having a type of assembly which does not allow relative motion between the two parts. So this is part one and this is part two, and there is no relative motion. If you are having a fit, if you can fit these two components together, it basically will ensure that the parts are going to rotate together. Everybody is following this much?
Yep.
Yep.
Yeah. Okay, now as a designer, what questions arise in your mind for this specific configuration and for this specific situation?
Professor, are you saying this the cylinder is bigger than the hole?
Yes.
Okay.
Yeah, that's what interference is, that there is an interference between the shaft and the hole that on this part.
How's it going to fit inside of it?
So That's a good question, that how to fit inside it. Obviously, if you want to slide this component together, it will not be, you will not be able to do that. So there are different ways of assemble these two parts together. You basically use a press fit, or basically press the two parts. You hold one part stationary and you press it. And what will happen that there will be, because the materials are elastic, there will be some deformation in the materials, and eventually they will actually get assembled together. So there will be some deformation from this part, it will slightly deform, and this will also slightly deform, and then they will stick together. Do you see what I'm saying here?
Yes.
So the reason that these two parts can be assembled together is, if they are rigid, they can never be assembled together. But because every material that you can think of, whether it is aluminum, whether it is steel, brass, copper, whatever material you think of that has got a specific elastic modulus, what does it? It means that it will elastically deform. And when it elastically deforms means, then when you're trying to press this part against this part, there will be slight deformation on this part, which is your hole, and there will be slight deformation on the shaft. Eventually they will, once you apply a force from a press, pushing force from here, this part will actually get assembled or stick inside this hole based on the type of interference you're going to get. Make sense?
Yes.
Great. Now, just to wrap up our discussion today, I know we are basically now coming to an end, and just a last question that I would like to ask you guys is to think as a designer. Suppose you are a designer, you are basically confronting this situation where you are basically having an interference fit between one component on another, let's say transmission shaft with a gear. As a designer, what are the different questions that should come in your mind for this type of situation?
Can you be like a little bit more specific, or can you repeat the question, please?
Yeah, so let's say you are working as a designer in a company, and there is a specific situation that you are given a drawing where you have an interference fit between two parts. This is a material A. Let's say this is aluminum. Shaft is made up of aluminum, and this gear is made up of steel. Two different materials. Of course, they are deformable, and you're trying to press this part against this part. What is going to happen?
You're trying to press them together?
Yes.
The materials would deform differently depending on how much force you
Perfect.
put on them.
Yeah, so as a designer, the first thing that comes to your mind is whether the material will be able to sustain that much force. You are putting that much force, pushing force. So this is a pushing force. So basically a pressing force that is applied to the press. So this is your press that you are using to have an interference fit. Now, by applying this pushing force, whether the materials are going to be compatible and have the deformation such that they can have the fit or not. So if you have aluminum and steel, there is no way you can do that, because aluminum is very soft. You try to push it, the aluminum will basically compress. It will buckle. It will not even go and slide against it. It will not do anything for the steel. If it is steel on steel, yes, because they have the same elastic modulus, they will try to go and they will try to deform in a similar fashion. So the first thing that actually comes to your mind is, okay, what is the material you are using and how much forces are being applied, what type of stresses are coming, whether the material can withstand the deformation, the stresses, and those are the questions that will come to your mind, isn't it? Right?
Yeah.
Yeah. So as a designer, the first thing that have to basically comes in our mind is whether the fit that is going to happen will cause some additional stresses in the material or the components, which will cause the failure of it. So even before performing its actual operation, because of this assembly sequence, the material will have excessive stresses, which will be counterproductive in the operation. So we need to figure out how to find the stresses that are going to generate in the two, because when these two parts are going to be joined together, you are basically clamping the two parts together. So there will be some clamping pressure. So whether the pressure is going to cause some stresses and cause some failure in the material or not, that's what we are going to learn, and we are going to discuss that in our next lecture. Another thing that is basically is coming is important is, let's say these two parts are assembled together, And I said that we require interference fit so that you do not have relative motion between number 1 and number 2. That means if number 1 is rotating at 10 RPM, number 2 is also rotating at 10 RPM. Are you guys with me on that part?
Yes.
Yeah. So in your opinion, when that rule or that condition will be violated, when I will have slippage. So basically it means that if I'm rotating at 10 RPM, but my part is going to rotate at less than 10 RPM, is that going to happen at any time? Will there be slippage or possibility of slippage at any time?
No.
Possibly.
Unless it's over, like you overforced it.
Yeah.
Yeah, if the material had some deformation.
Yeah, basically, see, who is preventing the relative slippage? What is
Wouldn't it-
preventing the relative slippage between this and this?
Friction.
The
Friction.
press bit.
It's a friction, right? Basically, you are clamping the two parts together. So, for example, this is one part, and this is another part, and I want to rotate it. What is preventing the relative rotation? It is the friction between the two surfaces, right?
Yeah.
And that friction is generated from what? From the clamping pressure. So if the two parts are getting assembled, there will be clamping pressure, and that pressure will generate the friction force. The more the pressure, the more the friction force will be, isn't it? To basically just to wrap up our discussion, I know it's beyond that class time, so sorry for that. But let's say there's a block resting on a floor, and you are applying or there's a normal reaction from the ground. So it has got a force, and the friction force, if it is trying to move this way, the friction force will be attached to this opposite direction. This is the direction of motion. And the amount of friction force is dependent on what? It is basically given by mu times n, coefficient of friction times normal reaction. The more the normal reaction, the more will be the friction force, right?
Yeah.
Yeah.
Exactly. So here also you are basically two parts are assembled together. So it basically is a situation like this. You have the two parts which are assembled together, and there is a clamping pressure that will be generated. The more the interference, the more the pressure would be inside the hub and the shaft. And the amount of pressure will define how much friction force would be there. And based on that, we will see when that slippage is going to happen. What will prevent the slippage? When that slippage, what is the condition of that slippage? So we will actually come to this discussion. I just basically wanted to point you or lead you to this topic to make sure that we are understanding the reason for going to the interference FETs and what are the consequences of the interference FETs for the component, what type of stresses are going to come, and how much the torque carrying capacity would be for interference FET. So those are the questions we will actually revisit in our next lecture, but hopefully this will give you an idea about the issues as a designer you need to worry about the interference FET. If it is clearance FET, you can see there is no point of, if there is a clearance fit between shaft and gear, they will never move actually, unless there is some pin or some another way you can set screw or some key ways or some other ways you are combining these two parts together. But if it is just interference, then how you are basically ensuring that the two parts are not having excessive deformation, they don't have excessive stresses, and there is a sufficient friction for the torque carrying capacity that designers would like. So we will discuss this topic in the next lecture.